Welcome to today's lecture on the research of the Institute of Geotechnical Engineering of the University of Stuttgart on the topic of filter rules for geosynthetics. Review of the application of the filter rules for geosynthetics based on a new experimental study. As an alternative to classic single or multi-layer mineral grain filters, you can see here at the left side, the use of geotextile filters has been gaining in popularity for several years. The basic filter parameters used in the current filter rules for dimensioning geotextile filters are, in particular, the characteristic opening size 90, the water permeability, and the thickness of the filter itself. The common filter rules for geosynthetics in the MGUKE datasheet on the use of geosynthetics in earthworks for road construction, three safety cases according to their levels of difficulty are differentiated. The dimensioning is carried out on the basis of the specification of limit values of the characteristic opening size according to these hydraulic safety cases. The aim of the research carried out by the Institute of Geotechnical Engineering at the University of Stuttgart was to investigate and review the filter rules of the MGUKE, in particular the defined limit ranges of the opening size, regarding to the current state of the art to avoid damage. The tests are basically divided into cyclic, long-term, and suspension experiments. In general, the test setup, shown here on the right side, consists of three plexiglass cylinders with an inner diameter of 12 centimeters and a head section. Between the first and the second plexiglass cylinder is the geotextile. Here you can see a big marked in red, which lies stress-free on a drainage gravel and a perforated plate for support. Above the geotextile, the soil sample is installed with a ratio of 1:1, means height in relation to the diameter. A load of 20 kilonewtons per square meter is applied to the soil sample via the head section. The hydraulic gradient can be regulated via an upper and a lower pressure tank. A reservoir, shown here on the lower side, provides a continuous water supply for the test setup. A total of 5 water pressure sensors, 3 in the soil sample and 1 each above and below, a flow meter and a temperature sensor were installed as measuring equipment. The soil particles passing through can settle in a tank at the base. Now I'd like to briefly manifest the key data of the long-term filter tests. The total duration of the 14 tests was 200 hours. In each case, a total of 7 geotextiles with 4 test soils were varied according the upper limit 090 max, here marked in green, and lower limit 090 min, marked in red. The test soils were narrowly graded sand, wide graded sand, slightly plastic silt, and a sand-clay mixture. In addition, there was a differentiation between the filter length, filter thickness, 1 or 3 millimeters, and the type of consolidation, needle and those with subsequent hardening. All this with the aim of the study, the long-term permeability development under constant boundary conditions depending on these parameters. Let's move on to some significant parts of the results. First of all, let's take a look at the permeability curves of the long-term tests of wide graded and narrowly graded sand. Overall, the most part, no filter stable system could be detected even after 200 hours of testing. This becomes visible by the future time variant decrease of the permeability. Occasionally, we see equilibrium tendencies when using the geotextiles at the upper limit of 90. It can also be identified that greater filter thickness lead to higher permeabilities. Mechanical non-woven geotextiles with subsequent calendering also behave more positive compared to the purely needled non-woven geotextiles. These results can also be applied to the other test soils. The wide-graded sand, the sensitivity to erosion leads to a strong and steady decrease in permeabilities and to strong rearrangement processes. So no filter stable system is achieved here. In addition to permeabilities, we want to take a look at the soil penetrations of the long-term tests for explanation. Here we see significantly higher soil inputs in the geotextiles at the lower limit. Higher inputs of the soil material into purely mechanical consolidated geotextiles occur. Also, the strong piping processes are reflected in the extreme bottom passage of the silt. The cyclic filter tests were basically performed with analogous boundary conditions and a variable hydraulic gradient. The test duration was 13 hours. The 5 load cycles with 3 load steps of 15 minutes each, you can see here on the right side, were applied to vary the hydraulic gradient. This series of tests is intended to provide information on the simulation of rain events and increase the fine particle mobilization in the soil. The flows over time of these systems using the geotextile at the upper boundary, all in green here, show a small decrease or even constant course of the flow. For this, however, comparatively larger passages must be accepted. A geotextile at the lower boundary, here marked all in red, on the other hand, provides for a significant decrease of the flow rate over time, which can be further manifested by greater soil incorporation into the geotextile itself, in some cases higher by a factor of 5. In comparison to the long-term tests, a clearly higher fine particles input into the geotextile is seen by variation of the hydraulic gradient. The suspension tests investigate the material transport by strong additional fine particle loading and had a time frame of 5 hours. The suspension homogenized by a mixer in the water reservoir was realized with the interval addition of kaolin 100 grams every 30 minutes. The suspension tests shown that an input of hydraulically mobilized fine particles into the soil must be avoided at all costs, regardless of the geotextile selected. The high loading of fines showed that the high risk of filter clogging, especially for the geotextile at the lower boundary. The filter tests carried out demonstrate very clearly the increased risk of colmation resulting from the geotextiles at the lower limit of 090 min. Particular danger arises from erosion, subfusion, prone soils with a strong tendency to clogging. Therefore, geotextile near the upper limit of 90 max should always be the first choice for permanently sufficient hydraulic permeability and to reduce the risk of filter failure. The lower limit of the opening size, according to ICSMGE, should be adjusted in this respect with attention to use of the geotextiles with an opening size at the lower limit. Based on the long-term filter tests, it would be even possible to increase the upper limit since only a small amount of soil discharge or passage through was registered in these tests. For the dimensioning of the geotextiles, the filtration length, like the geotextile thickness, should urgently play a role because the tests have shown that the geotextiles at the lower limit with a filtration length of 1 millimeter tend to clog even more. Suggestion here would be to use a criterion like as given by Mr. Stowese, that thickness D is 30 times of the opening size 090 itself. For dimensioning the consideration of further parameters by extending and further developments of the mechanical as well as the hydraulic criteria to the current state of the art would be essential to avoid further damage. Thank you very much for your attention.